Hey, nice to see you again. This is the final presentation in circle geometry, in that deductive geometry that we've been doing. And this is about summarising all the theorems on chords in circles and tangents to circles, and some of the earlier theorems as well. So can you see here, we've got a representative sort of group of diagrams here. Here's what we're talking about. This is a chord of a circle. A line joining 2 points on the circumference. Here we have what we call tangents. Okay, let's define a tangent. A tangent is a line drawn from a point where it just touches the circle at another point. Actually, only 1 point in common there between the line and the circle. It does not intersect like that. That would not be a tangent, because there'd be 2 points of contact here. A tangent has only 1 point of contact, a line with 1 point of contact with the circle. That's that one touching point. Tangents, if you like, touch the circle, do not intersect. So I guess you knew that. And here's a big mixture of tangents over here, just to confuse you. But what we're going to do now is finish off our deductive geometry in circles by looking at theorems regarding chords and tangents. Okay, so what we're going to do is summarise some that we know already and add some. Okay, the first one, the angle in a semicircle is a right angle. Reading it there. Okay, so a semicircle is the half of circle sitting on a diameter here. It's got to be sitting on a diameter. Then this angle out at the circumference is 90 degrees. We've seen that one before. Chords of a circle. Okay, let's have a look. The perpendicular from the centre of a circle to a chord bisects a chord. Let's have a look. Here's the centre. If this is coming out at 90, we are saying those two pieces will be equal. Okay, that's an interesting one. Now, we're not in this presentation going to prove that. But could you prove it? Okay, what could you do? You could use congruent triangles. You might like to try this. Enterprising young mathematician, congruent triangles. I think that's a radius. Is there another radius there? Would you have enough information for a congruent triangles proof? Gee, the congruent triangles have come in handy, haven't they, in this deductive geometry? Okay, what about the next theorem? The radius tangent theorem. The tangent to a circle is perpendicular to the radius at the point of contact. Let's see it. Here is a tangent. It's just touching the circle at the point of contact A. And the line from the centre, which is the radius, okay, the radius drawn to the point of contact is at 90. So this one in here is 90. That could be handy. That could be handy. Do you believe it? Could you prove it? What would you do to prove something like that? Could you use congruent triangles again? Don't know. We could take points out here and try to draw two triangles. You might have to think about a proof for that one. Okay, what about the last one? Tangents from an external point. Okay, tangents drawn from a point to a circle are equal in length. Okay, so if you draw this one in, it's got a point of contact at A, this one a point of contact at B, and they're supposed to be equal. You sort of can see it, can't you, about the symmetry or the roundness of the circle. It's going to happen. It's going to be even on either side. Could you prove that they are equal in length? Well, I don't know. Maybe here and here, congruent triangles again? I don't know, could you do that? Okay. Remembering that we now have a theorem that says that angle and that angle are 90. Angle between a tangent and the radius tangent theorem. That's this one up here. Maybe that will work. Do you want to have a go? See if you can prove it. Okay. Let's keep going then and see if we can use these theorems and a couple more. There's a couple more down below. We want to summarise what we've done before. So come down, let's have a look at this one, or these. Okay, so here's some of the ones we did before. The angle at the centre theorem, the angle at the centre of a circle is twice the angle on the circumference subtended by the same arc. So here it is, here's the arc, here's the angle at the centre sitting on it, and that is twice this one here. We proved that in the last presentation, so there we have it. This one we've seen also before. Angles subtended by the same arc on the circle are equal in size. So here's a piece of arc here, piece of circle. The angle standing on it, there or anywhere else around the circumference, will always be the same. Angles subtended by the same arc. So I know, are you used to that now? I was putting like this, angles subtended, same arc. Just an abbreviated little reason in brackets. Don't write the whole thing, it gets very cumbersome. Okay, the angle between a tangent and a chord. The angle between a tangent and a chord at the point of contact is equal to the angle subtended by the chord in the alternate segment. Oh, that's a mouthful. That's called angle between tangent and chord theorem. So what would you do? Angle between tangent and chord, something like that, some little abbreviation like that. Let's have a look at it. There's a tangent and there's a chord drawn at the point of contact A. And what this theorem is saying is this angle outside here equals the angle sitting on the chord in the alternate segment over there. Here's a little segment here, and the chord creates an angle at the circumference here in this other big segment. So that's a little tricky one. I might need to use that angle between the tangent and the chord theorem. Well, that's about it for this level. There are theorems regarding circles and concyclic points and things, which you do a bit later on. Okay, so are you happy with that? Let's see if we can do some problems on this now. So come down and let's practice our deductive reasoning. These screen clippings now are from Hayes and Harris, a textbook, and we're taking a few exercises from there. Okay, so here we are. We want to find x. Here, if AT is a tangent, they must tell you that that's just a touching point, so and A is a point of contact. And we've got two parallel lines here. So remember your basic procedure. That is, to draw a well-labelled diagram, put in all the information given on the diagram. Next step, look at the given information piece by piece and try to deduce something using theorems about that. So what's the book done here? They have chosen to go straight for the parallel lines. Okay, so going for the parallel lines, if you called angle CAT, that one, if we've got x up here. So therefore, angle CAT down here is also x. Alternate angles here between the parallel lines. Also, angle CAT, this one here, equals the angle in the alternate segment, equals ABC. Okay, angle between a tangent and a chord equals angle in an alternate segment. Now you don't have to put all these words in, you can just put up here alt angles will do. And here tangent chord theorem, something like that. Okay, so now we have in this triangle here, we have three angles, an x, and a 50 must come to 180 angles of a triangle. And as I was saying to you before, you could put that angles of a triangle. And so 2x equals 30, 130, subtracting 50 from both sides, and then dividing by 2. So look, some people like this and some people hate it. It's like a puzzle being put together, you have to do one piece at a time. So it can be quite fun. Other people find it restrictive. You've got to be a convergent thinker. Deductive reasoning, one fact after another, making deductions along the way. Okay, come down and let's have a go. Now, I thought in this presentation I might do it differently. Here are the answers over here. But I thought, so that you could see how it all works more clearly, I thought what we might do is you could pause the presentation, have a go at these three, copy the diagram into your book so you can work on it. Every time you put down a piece of information, put a reason in brackets, and then after that, come back to the presentation, because I'm going to go on now and put the actual solutions here. So pause it now so you don't see what I'm doing, and then come back. Alright, here we go. Let's do part A over here. In part A, what's the first thing that you notice? Well, the thing that springs to mind for me is the 40 degrees. So I'm going to say this angle here, let's call it alpha. Alpha is 40 degrees, angle alt segment. Alright, we're going to say, or what? Tangent chord theorem. Okay, one of those two, because it's the angle between a tangent and a chord, so you could do that. Look at the use of alpha rather than angle BAC. You could say angle BAC if you wished, equals 40, either of those. Okay, what's our next piece of information? So we've got alpha in here. What's our next piece of information? Oh, look at this. Nearly missed it. Let's write it down. AB equals AC. So that was given. Therefore, triangle ABC is isosceles by definition to equal sides. Therefore, angle ACB, using that notation, is X, isn't it? Base angles equal. Okay. Therefore, what have we got in this triangle here? In triangle ABC, X plus 40 is 180. What's that? Sum angles of a triangle. So 2x equals 140, adding up the x's, taking 40 from both sides, and therefore x equals 70 degrees, dividing both sides by 2. Do you like doing this or not? Interesting. Let's look at part B. My eyes go straight to the 70. So I'll use that piece of given information first. So I'll say over here, let's call that alpha 1. Alpha 1 equals 70, tangent chord theorem, or angle in alternate segment. Either of those statements are part of the theorem statement and guide the reader to the reason for your deduction. Okay, let's put an angle here, alpha 2, well, let's not do that yet, I better put in the reason first. So, AC equals CB given. Okay, so I want to pick up the next piece of given information and use it. So triangle ABC is isosceles. No reason needed there because that's the definition of isosceles triangle. Just covered it here. Okay, so now we can say this angle is equal because equal sides, the base angles of an isosceles triangle are equal. The angles opposite the equal sides. Therefore, we can say alpha 1 equals alpha 2 base angles. That will do. Base angles isosceles triangle. That's all you have to do is point the reader or the marker to the theorem with a clear enough statement to uniquely define the theorem you're looking at. Okay, so alpha 1 equals alpha 2. Therefore, 2 alpha plus x is 180. What? What are we doing? Sum of angles of that triangle. Sum angles of a triangle. Therefore, alpha is 70, so 140 plus x is 180, so x is 40 degrees, taking 140 from both sides. Okay, check it. It must have that sort of level of reasoning, reasons in brackets and making deductions. Okay, let's look at this one. This is a bit of a busier figure, so I don't know what we could do here. Don't know how to use a 70 yet. Let's have a look at this triangle OCT. I'm trying to use a theorem now because I'm going to use the idea of a tangent. That's a tangent. And there's a theorem about the angle between a tangent and a chord. So what we could say is angle OCT is 90 degrees. Tangent and radius, sorry, tangent and radius theorem. Tangent radius theorem. Angle between a tangent and the radius drawn at the point of contact. This is a radius, it's coming from the centre. Okay, so that angle in there now, I'll mark it in. Now they put down a reason for it. Don't splatter your diagram with all the things that you've worked out without using deductive reasoning and putting it down like this before you go to the next one. Alright, from that, what can I say? Well, I want to come up here to x. So maybe I should try to come up to up to t here in this triangle, working up the figure towards the thing I want. So let's try and find, what can we do? We can find this angle. So angle CTB in there, well, we've got 90 and 70, has to be 20 degrees, doesn't it? 160, so this is some angles of a triangle. So we've got this triangle sum. Alright, so let's just put in there, just tidy this up a bit. I'm getting carried away with all this. So, hang on, I'll just come there. So we've got angle CTB. This we can now say is 20. So we're going well. Now, what else can we do? Well, this is a bit hard now, it's a bit tricky. One thing, if you get stuck, because we've used the 70, we've used the tangent, don't forget it's a circle. So OB, here's the trick, OB equals OC equal radii. So that's the little trick you do in there. When you're in a circle, always remember, this is always going to be true. So don't overlook it. If the centre is marked, you've always got equal radii. So what can you say with that? Can you do anything if you've got those equal radii there? Does that help you? That might be useful. I think you can say, therefore, let's just rub this little bit out here. We can say that angle, or let's use alpha. Alpha 1 equals alpha 2. Alpha 1 equals alpha 2. Base angles, I haven't put isosceles in there yet. Isosceles triangle. Okay, should mention that OCB probably. Because I didn't put it in as I did over here. I didn't make an independent statement. That's okay. But as long as you cover it. Those two are equal, therefore these are equal. Now, therefore, 2 alpha plus 70 is 180. Some angles of that triangle here, OCB, you could put that in if you want. Okay, so this little triangle adds up to 180. So 2 alpha equals, taking 70, 110. Alpha equals 55 degrees. Oh boy, this is a little lot of work here. So let's rub this out and see what we're down to. Okay, so we've got this angle and we've got this angle. They are both 55. Can you see it? This is a special little theorem now. In this region up here, we've got 20, x is in there, and alpha's there. Can I just redraw that triangle? That's not quite right there. We'll just go here like this. So this is 55, that's x, and that's 20. Uh-oh, that's the exterior angle theorem, isn't it? When you extend the side of a triangle, the exterior angle is the angle that that extended side makes with the other side left there, and that equals the sum of the interior opposites. Do you remember that one? So x plus 20 equals 55, exterior angle theorem of a triangle. Okay, so x is 55 take 20, 35 degrees. Now that one is a fairly challenging one, because remember this step here, equal radii, easily overlooked, and lots of theorems involved in this one. Okay, how are you going? check your work, you must have the reasons, not just have the answers, because sometimes you can guess the answers by symmetry and so on. And we're about developing a deductive proof here in deductive geometry. Okay, come on down, let's have another go at some use of other theorems. So here's one here. A circle has a radius 4 centimetres and a chord of length 6. Find the shortest distance from the circle's centre to the chord. Okay, well, let's draw it in. There's a radius of 4, chord of length 6 here between A and B, so it is a chord, and that the x is the shortest distance from the circle centre to the chord. What that means is the shortest distance means the perpendicular distance, so don't forget to put that on your diagram. It's coming straight down, if you like, to the chord, perpendicular to the chord. So, what can you say? Oh, that's a theorem. So M is the midpoint of AB. What's the new theorem we've just had there? The perpendicular drawn from the centre to a chord bisects a chord. I would give a reason here differently. Line from centre. No, not line, sorry. I've left that out. Perpendicular from the centre to a chord bisects a chord, so we don't have to put all of it perpendicular from the centre, because that's the shortest distance. Okay, so therefore AM is 3. Well, why is AM 3? Well, the whole chord was 6, so it's now split it into half. That's going to be 3. So now, in this triangle, we can use Pythagoras. The square on the hypotenuse equals the sum of the squares on the other two sides. Okay, and then solving that, x squared is 7, x is plus or minus. Remember, when you're solving a quadratic, a negative times a negative is a positive, and a positive times positive is a positive. So there are always two possible solutions. You should put them in, then put the positive one, because you're saying x is a length here, it's got to be positive. So the shortest distance is root 7. Okay, so can you see when you have this perpendicular situation going on, and there's a few theorems that involve it, angle in a semicircle, angle between a tangent and a radius, that's a new one. This one here, a perpendicular drawn from the centre. So you could use Pythagoras whenever that comes up. So be on the lookout for that. That might be very useful. And here's some here. And I think, shall we do the same thing as we did in the last question? And that is, pause the presentation. You might have to do some constructions here, like making up triangles or something, because otherwise there's nothing to work in. Okay, so we need to work in closed figures, basically, in geometry. We've got a lot of theorems about quadrilaterals and triangles, but you need to create those triangles. So if you want to pause it now and have a go at all three, and then come back, and I'll be doing the work for you to show you the deductive steps. Okay, have a go. Right, here we are back again. Let's have a look at the construction here that we might use. We want to find x, and x is this little length in here. So, what can we say? Well, first of all, you can see I've joined up these because I want the radius, so I need to draw at least one radius. There's another one over there, but this one will do. This is 5 centimetres, line from the centre to any point on the circumference. So that's a 5. Now, so let's do some reasoning here. Let's call this ABC. So, in triangle ABC, AB equals 5. That's a radius. Okay, it's a radius. And also we can say BC equals 4 centimetres, perpendicular from the centre theorem, right? Because we're given that this is perpendicular, and perpendicular from the centre to a chord bisects the chord. Okay, so now what have we got? We've got a 5 and we've got 4. We should be able to find x. Let's just redraw the triangle perhaps. It looks like this now. That's 5, that was 90, that's 4, and that's x. Can you see it? Okay, so the square on the hypotenuse equals the sum of the squares on the other two sides by Pythagoras. Okay, should put that in brackets. Did I do it before? I'm not sure. So here, 25 equals x squared plus 16. Subtract 16 from both sides. 9 equals x squared plus or minus 3. It equals x, because remember, neg 3 by neg 3. Square neg 3, that's also 9. Therefore, x is 3 centimetres, because you must take the positive one, because it's a length. Length is only positive. No direction in that. Okay, did you get it? How are you going? Watch the deductive reasoning. Take pride in the argument you're putting up. Okay, let's look at this next figure now, part B. Well, we've got to do the same sort of thing. So let's draw it here and call this triangle A, B, C. And let's see what we can do with it. Well, first of all, in that triangle AB, so you don't have to put that, but it's nice. AB is 4 centimetres. And what's that? That's because it's a radius. So actually there's a good indicator that you have to join that up, because otherwise how can you use a radius of 4? And you must use all the given information. So AB is 4. Now, we've got AC is 3. Can we say something about BC? Yes, well, BC is x on 2. Why? Perpendicular from the centre theorem. Bisects the chord is what we don't have to write the whole thing in. What have we got? We've got the same thing as before. Here, just let's look at it. We've got this. This is x on 2. This is 4, and this is 3. So therefore, we lost that a bit here, so let's just go back up. So 4 squared, the square on the hypotenuse is the sum of the squares on the other two sides, which is Pythagoras. So 16 equals, square this, square the top line, x squared, square the bottom line, 4 plus 9. Subtract 9 from both sides. 7 equals x squared on 4, and then 20, multiply by sides by 4 to get back to x squared. 28 equals x squared. So the square root of 28 equals x, and it's plus or minus. We only want to take the positive one, since x is greater than 0. And square root of 28, the square root of 4 by 7, just running out of a bit of room here, so just come up a bit, is x. The root of 4 by root of 7 is x, or 2 root 7 centimetres equals x. Okay, a lot of work there. Okay. Notice here, if you can simplify that square root or surd form into a product of factors, one of which is a perfect square, like the 4, then you do it. If you can't, you just leave it as a square root expression. All right, let's have a look at this this one over here. I'll just come down a little bit. There we are. It's the same thing, isn't it? We need to use this radius, so let's join that in there. Call it A, B, C, or it could be really ABO, isn't it? It's a centre. In triangle ABO, we're given that that's a 90. So here, what can we say? AO is x, we've got that, we've got 2. Got to use this. So let's have a look. AB will be 5 centimetres. Same reason again. The perpendicular from the centre to the chord, perpendicular from centre theorem, bisects the chord. So therefore we've said that is 5. So let's draw what we've got here. We've got x, we've got 2, and we've got 5. Therefore a square on the hypotenuse equals the sum of the squares on the other two sides by Pythagoras. Therefore x squared is 25 plus 4. X squared is 29. X equals plus or minus root 29. Therefore x is root 29, because it's got to be a positive. Just slowly, carefully going through the logic, the deductive argument there. And we've got those answers summarised up there. All right, are you getting the hang of it? A few things coming together there. I hope you're enjoying this as a problem-solving exercise, recognising the pieces of the puzzle to put together, if you like. Okay, let's do a little bit more. Not much here now. I'll just check this one. The tangent from a point M to the circle. Here it is. Radius 5, so draw in the radius. Is 12 centimetres long, so that tangent is 12. Find the distance from M to the centre of the circle. Well, so that's OM. So first of all, OTM, they've marked it in here already, is 90. That's the radius tangent theorem. In other words, the radius drawn, I'll just scope some of this out, the radius here drawn to the point of contact, from the point of contact, so that's the radius there, is at 90 to the tangent. If you join the point of contact T to the centre, that's a radius, it's going to be perpendicular to the tangent. So therefore you can say square on the hypotenuse equals the sum of the squares of the other two sides. On the other two sides, that's 5 squared plus 12 squared, and it's 39, since it's got to be a positive. Okay, so that's a straightforward application of Pythagoras, just realising that that's the crucial result there, the radius tangent theorem. Okay, come down, and do you want to have a go? Now, these I'm going to do differently. I'll just give you the answers to these down below here. I won't work through them all. I think these aren't too bad. Just checking some of the theorems, the angle between a tangent and a chord equals the angle in the alternate segment. Check some of those. Check a few 90s here. See how you go putting your argument together. Now I'll just show you the answer. You can pause the presentation now and have a go at that. I'm not going to come back and do all the detailed arguments here. I'll just show you the solutions now. Or really not the solutions, the answers. Okay. So they are the 6 answers, A, B, C, D, E, F. Make sure you put those reasons in brackets. Okay, let's go on. Got a few more here. Now again, what we'll do is, I think A and B won't be too bad for you. So here are the answers over here with a couple of reasons. And you'll be able to see how to do those, I think. But one thing I do think I should do is question 7. It's a bit of an extended one. So what I'd like you to do is to pause the presentation now and see how you go with all 3 of these, 6A and B, and check your answers over there, and 7. And then I'm going to come back and do 7, because I think 7 needs a bit of explanation. Okay, so pause the presentation, have a go. Right, coming back now, let's have a look at this one. I need a bit of room here. We need to deduce that AB plus CD equals BC plus AD. That's interesting. AB plus CD equals BC plus AD. That's unusual. I don't know a theorem for that. Okay, so let's have a look now at AB plus CD. So often a good way of handling a problem like this is to start with the left-hand side. And you don't put the equals in, you have to show that equals. So I'm going to start with the left-hand side and unpack it. So AB, what can I say about AB? Well, it's something to do with distance of tangents from a common point. So let's say that AB is AP, so that's that tangent from there to there, plus BP, that's this one here. And you might say, well, Huddy, why didn't you call it PB? Why didn't I call it just AP plus PB? Well, I've recognised that the only theorem I can use here is the fact that tangents drawn from a point to a circle, the two tangents are always equal. So I'm going to think of all of them as BP and BQ, right? So I can identify that. Okay, this is an answer for AB. Now let's do CD. So let's just tidy this up. So CD done the same way, it's down here, is CR CR, that's a tangent from there, plus DR, writing them as tangents from a point. Okay, so that's AB plus CD. So let's do BC plus AD in the same way. Okay, so BC, this is this line, is BQ plus CQ. Okay, I'm doing BQ plus CQ, same reasoning before as looking at them as coming from an external point as a tangent to the circle, so you use that theorem. And then AD here will be AS plus DS. Okay. Alright, well they don't look much like each other, but what we can say here is BQ is the same as BP. Up here, BQ is the same as BP. What's the reason for that? Tangents drawn from a common point, if you like. Let's go through and modify all these now. So what's CQ is equal to CR, watch it here, CQ, the other tangent drawn from this common point is CR, so I'm going to replace this, and then AS up here is the same as AP, I'm going to replace that, and then DS is the same as DR. And we have to put the reason there, tangents from common point theorem, something like that, are equal in length. That all four of those have been replaced under the same theorem. So let's reorganise it. Put AP in front, then BP, and then CR, and then DR. Uh-oh, can you see it? It's the same as that. Equals AB plus CD, and in brackets as required. That's what we like. Okay. Historically in maths we've used several things to indicate the solution is complete, that we've proven what was required. Historically, it used to be a long time ago, quad erat demonstrandum, QED. Quad erat demonstrandum, which was required to be proven in Latin, is what that is. And then it went to RTP, which was short for required to be proven. Again, a statement say, hey, I've done it, I've finished. And now we've got as required. It's the modern version of that. So when they ask you to do something or prove something and you complete it, it is customary to put one of those three, and the modern one is as required. Okay, look, I hope you've enjoyed deductive geometry. Some will, some won't. The idea of putting the pieces of a puzzle together and coming to a deduction at the end about some property. Okay, look, well done with the geometry unit. I hope you're happy with the skills you've attained there, and I hope to see you again in another presentation. Cheers.